Hey. Number 30 says a Jupiter-sized planet orbits the star 55 Cancri with the orbital radius of 8.2 times 10 to the 11 meters. See figure 9.31. The orbital period of this planet is 13 years. What is the mass of the star that it orbits, and how does this compare with the mass of the sun? So they gave us for number 30 a radius that's equal to 8.2 times 10 to the 11 meters. And they told us that the period is equal to 13 years. What's probably the first thing that you want to do with these numbers? Make sure that they're in SI. Is the first one in SI units? Yep. Second one, is that SI units? No. How do we convert it to SI? Convert it. What do we need to convert it into?
Seconds.
Seconds. How do we convert that into seconds?
Here's the days, days, the hours.
1 year is how many days? 365. 1 day is how many seconds? 24 hours. 1 hour is how many seconds? 3,600. There's your 3,600 Adaris. Okay. Be missing a little bit. Okay. So we can multiply this together. I happen to not actually multiply it until I did the final calculation, so let's bust out the calculator. 13 times 365 times 24 times 3,600. And what do you get? 4.1 times 10 to the 8th seconds. So now I have period in seconds. And apparently, based on these two numbers, we can calculate the mass of the thing we're orbiting. How do we do that? That is a good question. That's what they asked us. So how do we figure this out? Yeah. You can equation for V? What equation? There's a bunch of different equations. There's several. The one that's probably easiest to use. So if you go through the textbook, and this is what I recommend on your equation sheets, just write down all the equations from the chapter summaries. You'll find this equation. This is the equation for the period of orbit around the sun. So we're going to write this down. It's t squared equals 4 times pi squared over g times mass of the sun, r cubed. This is somebody's law. Whose law is this? Tom's? It's Kepler. Kepler's third law. P squared equals semi-major axis cubed. Okay? We could derive this using the velocity equation. So we could get this another way if we didn't have this written on our equation sheets. But this is for orbiting the sun. Am I orbiting the sun? No. What am I orbiting? Let's read again. A Jupiter-sized planet orbits the star 55 Cancri. So what am I orbiting? Star 55 Cancri. Okay. So I need to figure out what the mass of the star that I'm orbiting is, what the mass of 55 Cancri is. I have the period of my orbit. I have t. Let's see, what else do I need? 4. Do I know what 4 is?
Yes.
Yeah. Do I know what pi is?
Yes.
Pi squared?
Yeah.
Yeah. How about g?
Yes.
Yeah, we know what big G is. What's big G? Don't say 9.8. Big G is gravitational constant, 6.67 times 10 to the negative 11. Commit that to memory. No, put that on your equation sheet. If you don't know that, I would give that. You just said it out loud. MS. Do I know what MS is? Multiple sclerosis. What's that mean?
Oh my god.
What are you trying to find?
Mass of the sun, but we're not orbiting the sun. What are we orbiting?
The star.
We're orbiting a different star. So this would be the mass of the star. This works for any planet orbiting any star. You just plug in the mass of the star that you're orbiting. Do we know the mass of the star?
No.
Yeah. No. Yeah, we do. Wait, no, we don't.
No, we don't.
We do not.
We do not. Okay? How about R? Do we know the radius? How far away the star is? So we know everything except for MS. So we do algebra to solve this for MS. So multiply MS to the other side and divide by t squared. And you'll find MS equals 4 times pi squared times r cubed divided by g times big T squared. So that was algebra. We do this algebra and we find MS equals 4 times pi squared times r cubed. R is 8.2 times 10 to the 11 cubed. Where did that come from again? That was given. That's how far away my planet is as it orbits this star. Divided by 6.67 times 10 to the negative 11. That's what big G is. Do you have to memorize that? No, I'll give that to you. Put it on your cheat sheet if you don't remember. T is 4.1 times 10 to the 8 squared. Plug in all those numbers, you'll find the mass of this star is 1.9 times 10 to the 30 kilograms. And then they want to know, how does that mass compare to the mass of the sun? Mass of the sun is 1.9 times 10 to the 30 kilograms. So how does that compare? It's the same. That's all they want you to know. It's about the same mass as the sun.
Can we solve this a different way? Because there's a different way you did it.
There's all sorts of
There's,
different
like,
ways you can solve it.
right? Okay, cool.
This is just the easiest one,
Just wanted to ask.
if you have that equation.
Got it.
Yeah. You're welcome. I'm here to help. Sometimes. Sometimes I'm here to make your lives miserable. Any questions on that one? Okay. Okay. Let's do number 56. Number 56, we have an artificial satellite of 1,300 kilograms made of aluminum, is in a circular orbit at a height of 100 kilometers above the surface of the Earth. Atmospheric friction removes energy from the satellite and causes it to spiral downward so that it ultimately crashes into the ground. Does this actually happen? Everybody seen the movie Gravity?
No.
So this is basically what happens in Gravity. We should have just watched Gravity today.
You know,
Yeah, that would have been a great idea.
I mean,
This
it's
is
not
a great idea. It's never too late. Maybe we'll watch Gravity after we're done with the rest of it. You don't want to fall asleep? You were in my Discover class. We watched Gravity in there, didn't we? See, that's why Catherine was a good student in my Discover class. Paris back there? Horrible. Horrible. Okay.
I paid attention. And I was going to the best presentation, so shush.
Okay. Okay, put in my place. I get such respect. Number 56. So this artificial satellite has a mass of 1,300 kilograms. And it's orbiting at a height of 100 kilometers above the surface of Earth. So other relevant numbers, we're orbiting the Earth, so we probably want to know characteristics of the Earth too. This would be true for anything that you were orbiting. So if I had this, maybe I'd give you a problem based on the big event that happened earlier this week. What big thing happened earlier this week about space? Anybody see this? Oh. Say it. Yeah? Yeah. What about Mars? We landed on Mars. We landed. Do you know how hard it is to land on Mars by any chance?
Easiest to float in the air.
Let me pause.
Yeah.
So
There's
maybe-
a picture of them happy.
Yeah, yeah. Picture of happy nerds. So maybe
Paid a lot of
we could do a problem like this for Mars. So instead of the mass of Earth, we'd use mass of Mars. Mass of Earth is 5.98 times 10 to the 24, number that we all know off the top of our heads, I'm sure. And the radius of Earth, 6.378 times 10 to the 6 meters. So there's our Earth. There's 378. That's a 3. They should judge my writing. It's because I'm a doctor. There's my satellite orbiting. It's going to lose energy due to friction, and it's going to spiral down, and it's going to crash into the Earth. It's a beautiful picture, isn't it? You could just see the motion. And then we'll make it really relevant.
Oh, wow. Nice.
And there's our astronaut.
I don't know.
Did I?
She's not, yeah, she's not Romeo and Juliet.
We're going to change your last name too to make it even more French.
Juliet Baguette.
Astronaut
A
Juliet
rhyme.
Baguette. We need a little tilde over that too. And I feel like you should have a little hat.
A beret.
Yeah, I can't draw berets very well. There's a beret. And I think you also need
A baguette.
one of those long cigarette things.
Actually, it looks like
Yeah.
a gangster.
Yeah.
Oh my god, Odie!
What?
Oh my god.
Okay.
First no bonbon.
So Juliet Baguette is on the artificial satellite that's losing energy due to friction. We need to calculate what is the initial orbital energy, gravitational plus kinetic of the satellite, what's the final energy when the satellite hits the ground, and what is the energy change. So how do I find the total energy of something orbiting? The total energy is made up of gravitational energy plus kinetic energy. U, gravitational energy is negative G times M over R E. This is the gravitational potential energy of two things orbiting. Big G, what's big G? Universal gravitational constant. So what if I go to Mars? Does big G change? No. What if I go to the other side of the universe? Does big G change? No. No. Why?
There's a constant.
Universal constant. Okay. Little m. What's little m?
That one.
Mass of the satellite. What's big M? Mass of Earth. What's RE? Radius of Earth. Is the radius of the Earth? So this is the radius of where I'm orbiting. Where am I orbiting? Am I orbiting at the radius of Earth? No. Where am I orbiting? Radius of the Earth plus 100 kilometers. So we have to do RE plus the height that I'm orbiting at. Yeah?
Wait, why? Because we're not at that low.
We're not, the radius of Earth is the surface of Earth.
And we're not
So
there.
that's if we were talking about Juliet right now.
Okay.
We're talking about Juliet floating around 100 kilometers above our atmosphere. Yeah. Okay. Plus kinetic energy. What is kinetic energy? 1/2 mass times velocity squared. How do I know which mass? How do I know it's little m and not big M? Energy of the satellite. The satellite's moving. Earth is not. Okay. So I need to find what V is. I know what big G is. I know what little m is. I know what big M is. I know RE. I know H. I know little m. I need V. Velocity of something orbiting. This is the square root of equation that we were talking about earlier. Square root of big G times ME over RE plus H. So I can plug this in right here. I get my E total equals negative G times little m times big ME over RE plus H plus 1/2 times little m times big G times M sub E over RE plus H square root squared. Oh snap. We blew the mind of the math major. So E total, this is crazy. You're all gonna flip out when you see this. So I square this, I got a G times an ME over RE plus H. So I squared that. Get this. These look really, really similar, don't they?
Yep.
Wow, stuff, man.
Are they the same thing?
Well, I mean, you have to subtract.
We've got to do a few things first, don't we?
So this is 2 over 2 is still 1, right? So I'm putting them both over the same denominator. So negative 2/2 plus 1/2 give me what? Negative 1/2. So the total energy I have is negative 1/2 big G times little m times big M over RE plus H. You know all those numbers, so you can plug them in and you can find the energy total is equal to negative 1/2 times big G times little m times big M over RE plus H. And plug all those numbers in, you'll get negative 4 times 10 to the 10 joules. Now the nice thing about this equation, this is a general equation. I didn't make any assumptions when I was figuring this out. This is what professors typically do in physics classes. They spend the whole class deriving this equation and then telling you, whoa, look, now you can just use this. In my physics class, the teacher actually spent an entire lecture getting to this equation. I spent, what, like 5 minutes getting you there? So you can use this. Anytime you're asked, what's the total energy of something orbiting? There it is. Use that equation. Negative 1/2 G MM over the height, the distance that you are from the center of your object. So we can use that equation again to figure out what is the energy of this thing on the ground. So E total on the ground. Let's see what changes. I have a negative 1/2. That's not going to change. Big G. That's not going to change. Mass isn't going to change. Big mass isn't going to change. Divided by the radius. So this is the distance you are from the center of the object you're rotating around. If I'm on the surface, what's my radius? Is it RE plus H?
No, it's just RE.
Just RE. So now I just have RE. No need to add H because I'm not orbiting high above the surface. Plug in your numbers here. You'll get E total on the ground. That's equal to negative 8.14 times 10 to the 10 joules. How do I find the total energy? Or the total energy loss, I think, is the next thing they ask. What is the energy change? Subtract?
Yeah.
Yeah, which one do I subtract from which one? What's my final energy? Am I starting out, is my final position in orbit or is my final position on the ground? Ground. So I take the energy on the ground minus the energy in orbit. So it's negative 8.14 times 10 to the 10 minus negative 4 times 10 to the 10. Take that difference, your change in energy will be negative 4.13 times 10 to the 10 joules. It's going to be negative because your energy is being lost. Any questions on that part? No? So now the tricky part is something that we've never talked about. Suppose that all this energy is absorbed in the form of heat by the material of the satellite. Is this enough heat to melt the satellite? And is this enough heat to vaporize the satellite? And they tell you the heats of fusion and vaporization of aluminum are given in table 20.4. When they say heat of fusion, that means the heat to melt. Heat of vaporization is heat to vaporize. So they give you those numbers in this table. I would give you those numbers as well. They give you the aluminum, we'll call it melt. Heat is equal to 3.99 times 10 to the 5 joules per kilogram. And the aluminum vapor, to vaporize this satellite, is equal to 1.05 times 10 to the 7 joules per kilogram. Now I need to figure out how much energy is it going to take to melt my satellite. This tells you you need 3.99 times 10 to the 5 joules per kilogram of weight to melt this. So how do I figure out how much energy I need to melt the whole satellite? How do I figure it out?
Use the mass of the satellite.
Okay, how do I use that?
You convert it to how many joules it takes.
How do I convert the mass of the satellite into joules?
Multiply that.
Multiply this times the mass of the satellite. That gives you the joules to melt that specific satellite. So multiply this by 1,300. 1,300 kilograms. Kilograms cancel out. And I get 5.19 times 10 to the 8th joules to melt. Is there enough energy lost by the satellite to melt it? If all that energy goes into heat, can this satellite melt? How much energy went into heat? 4.13 times 10 to the 10 joules. Is that more than 5.19 times 10 to the 8?
Yes.
Yes. 10 to the 10 is bigger than 10 to the 8.
Okay, yes.
So more heat, so there's enough heat to melt this satellite. So the satellite, as it flies down, it's going to crash, it's going to melt. Does that mean that it's gone, that it completely disappears?
No.
It just means it's melted, so you get a melty chunk of metal that crashes into you. Let's see if it vaporizes. So vaporizing will completely destroy the satellite. Take your 1.05 times 10 to the 7, multiply by 1,300, and what do we get there? I get 1.37 times 10 to the 10 joules. Is that enough? Is there enough energy being lost to actually vaporize this? Yeah. Is there a significant energy difference? Do we have a large margin of error, let's say? How much extra energy do we have? We could vaporize this how many times over? About 3 times over. So we got plenty of energy. So when we're designing satellites, the materials that we use, we take this into account. So that if something goes wrong and the thing crashes into the Earth, it's going to get vaporized. Because we don't want it to crash and kill people. That'd be bad. There's a video on YouTube about the only woman that is confirmed to have been hit by a meteorite, by a chunk of rock that came through the Earth and made it through. Broke her leg. Yeah. You know what's really sad about that? She didn't get to keep the rock. She was renting a house, and the people that owned the house said that they owned the rock. So they own the house.
She owns her leg.
She owns her leg, but the rock ended up landing on her, smashing her leg and landing in the house. So it's their property.
Wow.
She ended up having to buy the rock from them. The rock that broke her leg. That ain't right,
So,
right?
yeah.
That's so
Well, why
wrong.
would she buy a
She
rock?
was gypped. Also true though.
It's a good question. How many of you, if you were hit in the leg with a rock from space, would want to own that rock?
You know what? Maybe, yeah.
How many wouldn't buy the rock?
I don't know.
How much?
These are the practical people.
I have $4.
Yeah.
And then it's a rock that would bring back memories.
The other question that I was asked was chapter 16, number 58. Chapter 16, number 58. So this is all about waves. Number 58, we have a string that's fixed at both ends, has a resonant frequency of 660 hertz, and also a resonant frequency of 440 hertz, but no resonant frequencies at any intermediate value. Identify what overtones these frequencies correspond to, and deduce the fundamental frequency of the string. So we have some equations that let us tell about resonance. We have a general equation that we derived at one point. We have some frequency, some resonant frequency. F sub n is n times the fundamental frequency. This is a general equation, we know that. So we can use that for this one. We know that we have 400 hertz is the resonant, or 440 hertz, I think, is the resonant frequency that we're hearing. So we can just call that is the n times f sub 1. I have two variables that I don't know. Anytime there's two variables that you don't know, you're going to probably have to find a second equation and set those two equations equal to each other. Okay? That's kind of a clue of what you'll need to do. So we need another equation. The other number they gave us was, what did they give us? 660? So we have another resonant frequency at 660. And we know that there's no resonant frequencies in between these two. And resonant frequencies are based entirely on these ends. So the first resonant frequency is 1 times f sub 1. Second one is 2 times f sub 1. Third one is 3 times f sub 1. Fourth one is 4 times f sub 1, so on and so forth, right? So whatever n this is, I know this n has to be 1 greater than that, because it's the next greater frequency, next greater harmonic. So this has to be n plus 1 times f sub 1. Yeah? So now, how many equations do I have? 2 equations. How many unknowns do I have? 2 unknowns. Anytime you're having this situation, 2 unknowns in an equation, you're going to have to get 2 equations, 2 unknowns, and set some things equal to each other. Okay. Now we need to figure out, what do we want to set equal to each other? What do we want to solve for? Do we want to solve for n, or do we want to solve for f sub 1? Which one would be easier? You think
F
n
sub
is easier to solve for n?
Yeah.
So get rid of f sub 1?
Yeah.
Yeah? How do you get that?
Divide and
Well, how do you get that f1 is going to be easier to
It's
plug
not-
in for?
It's just like n. Like there's no like plus one, minus two, whatever. You just divide the number that you get.
So f sub 1 is all alone, and I have a plus 1 that's associated with it. So whatever's all alone is usually going to be easier to plug in for. So I can solve, which equation do I want to solve for f sub 1 to plug into the other? Do I want to solve the equation on the left or the equation on the right? Left. How do we pick that?
Because it doesn't have the plus 1.
It doesn't have the plus 1.
That's what I.
No parentheses, very simple equation. So we'll use the one on the left and find f sub 1 equals 440 divided by n. Then I can take this and I can plug it in to my second equation. 660 equals n plus 1 times 440 divided by n. Okay, how do I solve this for n?
Oh. distribute?
So I could multiply this into everything, but then I still have a fraction. I hate fractions. How many of you hate fractions? They're awful. I want to get rid of them. So I can multiply the n to the other side and get rid of all fractions. So that's what I would do first. Multiply both sides by n. So I have 660n equals n plus 1 times 440. Then I have 660n equals 440n plus 440. Subtract 440 from both sides. (220n) equals 440. N equals 2. (440) n equals 2. So which harmonic is this? N equals 2 is what harmonic? Second harmonic. What overtone? First overtone. Harmonic is some multiple of the fundamental frequency. So there's a fundamental one, and then there's ones above that. And we can show you, we'll show you this on the string again. Okay. No? Okay. We won't.
Yes.
No. We'll show you on the string again. We'll use a strobe light too. That'll be great. So you have a fundamental frequency. That's when you can get the very first wave that you see on a string. Something that looks like. If I have a string at both ends, I have one little lump. That'd be the fundamental. And then I can have a wave that actually looks like a full wave. Then I can have up, down, up, something like that. Each one of these is a harmonic of the fundamental frequency. So the fundamental frequency n equals 1. That's the first harmonic. N equals 2 is 2 times the first harmonic. It's the second harmonic. But it's also sometimes described as one tone over the fundamental harmonic. So this would be the first overtone. These are the same thing, 2 different ways to describe the same exact thing. No? Okay? Okay. So that is number 58. Those are all the questions that were asked about for a review. Do we have any other questions? Is the test going to be hard? I never think my tests are hard.
Of course.
What'd you say? Are they from the quizzes? They are similar to the quiz questions. They're not exactly the same, but the same format. Yes.
How many of the 50 chapters?
I don't. I think it's like one on each chapter.
So it'd probably be more than last year.
A little bit longer than last time. Which should be better at solving physics problems. So. You might not be, but you should be.
That was good. That was a good one, Dr. Brown.
Yeah. And YouTube caught me insulting my students. Good.